Here are a few examples of using the product rule and quotient rule for logarithms. So let's start out by evaluating log base 15 of 3 plus log base 15 of 75. So you might first think about evaluating this directly, but if you try to think of what power on 15 would produce 3 in order to evaluate log base 15 of 3, well, there's no nice exponent that you could put on 15 to produce 3. So whatever this first logarithm is, it's not going to be very nice. So that might make you think, well, maybe I should look for some other options. And with logarithms, there are usually options for how to write what the expression is. Since these two logarithms are being added, you might try to think of what do you know about when you have two logarithms with the same base that are added together like this. Well, the product rule for logarithms says that this is the same as log base a of b times c. That should be a c. So a product inside a logarithm is the same as a sum outside a logarithm. This really corresponds to the fact that a sum in an exponent is a product outside of the exponent. Well, since logs are inverses for exponents, this is basically the same rule, but the other way around. Instead of a sum inside and a product outside, it's a product inside and a sum outside. Okay, we have a sum outside. We have a sum of two logarithms that have the same base. So we can use this product to sum property of logarithms to put these two logarithms together. We get log base 15 of 3 times 75. And 3 times 75, that's something that we can work out without too much trouble. It turns out to be 225. And what power of 15 is 225? Well, if it's going to be any nice power, it's bigger than 1, but so it maybe is 2 or 3. And if you check, 15 squared is 255. So what power would you put on 15 to get 225? That would be the second power. So this expression with two log base 15s, it looks really bad at first, but in fact, it's just 2. All right, let's look at another example. Let's expand the natural log of x times y. Well, for this one, this time we have a product inside our logarithm, and one option that you have if you have a product inside a logarithm is to split this into two separate logarithms. Our two separate logarithms will have the same base, so remember natural log is really log base e. So since it's a sum inside, it turns into a product, since it's a product inside the logarithm, it turns into a sum outside the logarithms. And it's the sum of natural log of x and natural log of y. All right. Which of these two ways of writing it as natural log of a product or a sum of two natural logs, which of these is better really depends on what you're going to do with this expression. Sometimes the first one is better and sometimes the second one is better. And so we need to be aware that you can switch from one to the other using this sum to product property of logarithms. Okay, let's look at a third example. Let's evaluate log base 3 of 27 divided by 1/3. So again, if we worked hard enough, we could evaluate this directly. We'd have to simplify this complicated fraction here. But since this is log of a quotient, you might have the idea that maybe there is a property of logarithms involving a quotient inside. And sure enough, there is. It looks like this. Log base a of b over c is log base a of b, the numerator, minus log base a of c, the denominator. Again, this looks sort of similar to a fact about exponents. For logarithms, a quotient inside is a difference outside, and for exponents, it's the other way around. For exponents, a difference inside is a quotient outside. So same idea, but in the opposite direction because logs are inverses for exponentials. Okay, since we have a quotient inside, we can use this quotient to difference property of logarithms to rewrite our log. This is log base 3 of 27 minus log base 3 of a third. Okay, log base 3 of 27. Let's see, what power of 3 would give us 27? That's the third power. 3 cubed is 27 minus, and then what power of 3 would give us a third? That's minus 1, since 3 to the minus first is a third. And now we just have some arithmetic to do. This is 4. Okay, let's look at one last example. Let's evaluate log base 2 of 6 minus log base 2 of 12. So if you think about evaluating this directly, what power of 2 would give you 6? There's some power of 2 that would give you 6, but it's not a very nice power, so the best we could do is to approximate log base 2 of 6. Same thing for log base 2 of 12. So individually, these logarithms are pretty nasty. But since we have a difference of two logarithms, and these logarithms have the same base, we can use the quotient to difference property of logarithms. So a difference outside is the same as a quotient inside. So we can write this as log base 2 of 6 divided by 12. Again, the logarithm that's negative is the one that ends up in the denominator. But 6 divided by 12, that's an easy one. That's a half. And log base 2 of a half, what power on 2 would give us a half? That would be minus 1. All right, so using the quotient to difference property of logarithms makes this one pretty straightforward. Now let's finish this off with a warning. Let's try to simplify one last logarithm. Let's simplify log base 2 of, say, x plus 2. So looking at something like this, we're so used to, on the one hand, using properties of logarithms to mess around with the stuff inside of the logarithm, and also we're so used to distributing things that it's easy to think that, hey, couldn't we write this as log base 2 of x plus log base 2 of 2? Is that right? Well, if you look at this has a sum inside and outside, but that can't be right. When a sum is outside a logarithm, inside the logarithm you should have a product. So these two things are definitely not the same. So this is wrong. So you might go flipping through a math book looking for some rule about logarithms that has a sum on the inside. And what you'll find is that there isn't a fact about a property of logarithms that has a sum on the inside. We are actually stuck with this expression. It's already as simplified as it can get. The moral of the story here is, don't try so hard to simplify logarithms that you make a mistake.